Great, thank you, and thanks for the invitation to be here. So I want to, I guess, start by drawing a little picture of some of my kind of understanding as an algebraic geometer of some of the words that are in my title. So what do I mean by that? So let's start. Suppose we start with some smooth projective variety over some number field f. Right? We can associate to this algebraic variety a Galois representation given just by letting the Galois group of f act on the étale cohomology of my variety. Right? Okay. And now the Langlands whole philosophy tells me that to this Galois representation, I should be able to associate something called an automorphic representation, right? Which I'm not going to say what it is, but we'll just call it f. And what I mean by that there's a correspondence between these Galois representations and these automorphic representations is that okay, to each of these things I can attach something called an L function, which is a meromorphic function on some upper complex half plane. And so if I take the L function of my Galois representation and I take the L function of my automorphic representation, to say that these two things correspond says that these two things are equal. And if my Galois representation came from a projective variety in this way, I'll write that this L function right here is the same as the L function attached to the variety. Okay? But somehow implicit in what I just said is another idea, right? Which is that suppose I'm handed some Galois representation, how might I know when that Galois representation is geometric, right? Or what does it even mean for that Galois representation to be geometric? If I hand you some Galois representation like this, this is described by sort of the philosophy of the Fontaine-Mazur conjecture, which says what kind of Galois representation should arise geometrically. Okay? But what do I mean? I have to make precise a little bit more what I mean when I say that this Galois representation arises geometrically. Right? So naively you might say, well, a Galois representation arises geometrically if the representation is the action of some Galois group acting on the étale cohomology of some variety, right? But I want to allow for a more motivic construction of what it means to arise geometrically. So let me say a little bit about what I mean, right? So meaning I don't want to just allow for a smooth projective variety to go right here, but I want to allow for here, this is a Chow motive over my number field f. Okay, so what I mean here, right, let me just review that I'll denote by this the category of Chow motives. Right, so here the objects are pairs of x, comma, e, where x is some smooth projective variety over f, and e is some element of cycles up to rational equivalence on x cross x such that e squared is equal to e. Right, so I can think of E as inducing some morphism on the cycles of X in the sense that if I take some algebraic cycle on my variety X, I can pull it back to this product, X cross X. I then intersect it with my E and then push it forward onto the other factor of X. And that will give me some new cycle on X. Right, so it takes cycles on X and sends them to other cycles on X. And so I guess I should say that morphisms, right, are given by if I have say, some x1, e1, x2, e2, then morphisms between them are just given by, I do e1, I then do something in an of x1, x2, where n is the dimension of x1, and then I do e2, right? And by the same process, you can convince yourself that this really does give me some kind of morphism from cycles on x1 to cycles on x2. Right, and so the idea of this motivic philosophy somehow is that it allows me to cut out subsets of the cohomology of X that behave nicely no matter what cohomology theory I use. Right, so, okay. And so I'll say that my Galois representation arises geometrically if it arises, so what I mean, sorry, is that if I have then some motive, x comma e, right, I can, in particular, look at its étale cohomology. Right, and this will come with an action by this Galois group. And so, in particular, I can attach to it some L function. So the L function that I'll attach to my motive will just be the L function attached to this Galois representation. Call it V. Right, and so what one wants to understand somehow in this picture is both how to go this way and how to go that way in this series of correspondences. And so in particular, what's often called a modularity theorem is something that goes this way, in a sense, in this picture. Right, so it starts with something, so it starts with, say, a motive, M, and identifies an automorphic representation F such that the L function of this M is equal to the L function of this automorphic representation. Right, so the most famous example of such a result is what's often called the modularity theorem of Wiles, which did this for any elliptic curve, or I should say Wiles plus many other people, right? Did this for any elliptic curve over Q. And as many people know, this was sort of the crucial ingredient needed to then prove Fermat's last theorem. But this will, for the moment, we'll put this sort of result aside for the moment, and instead think about sort of the opposite direction of this kind of theorem, right? So question, ask, this is sort of motivation. Given an automorphic representation, can one find, say, a Chow motive M such that we have this equality of L functions? Okay, and so for today, and so I should say there has been some work on this direction looking at some weaker notions of motives, right? So I've defined the category of Chow motives to be the category where we're really working with cycles defined up to rational equivalence. But we can relax this notion of rational equivalence for other kinds of equivalence, which will give us new notions of categories of motives that are oftentimes a little bit easier to work with. So they often have nicer properties, or cycles up to that are easier to find, right? But somehow, the notion of rational equivalence was what Grothendieck sort of envisioned when he envisioned this category of motives. And one reason why we might want to work with equivalence as opposed to any other notion of equivalence is because rational equivalence is the one sort of notion of equivalence that behaves nicely in families. And as algebraic geometers, somehow being able to do things nicely in families is of crucial importance. Right? So rational equivalence, for instance, has the property that if something is rationally equivalent to 0 on one fiber of a family, you can actually extend that to some open set, which is not a property that other notions of equivalence satisfy. So that this rational equivalence is somehow really the gold standard that we would like to use, but oftentimes we aren't able to for one reason or another. Okay, and so for today, I want to focus on this kind of question, but rather than think about arbitrary automorphic representations, I want to focus on a particular class of much easier automorphic representation called Hecke characters. Right, so these are continuous homomorphisms from the ring of Adels of some number field to C star. So here, right, maybe my audience today is a little more arithmetically inclined, so I don't know if I should define what the ring of Adels is or if everybody is familiar with that, but I'll just say it anyway. But okay, so what do I think of the ring of Adels as being, right, is I think of, let's take my number field K, and let's think of all the primes of K, right? And now let's think of tuples indexed by these primes. And so then an element of my Adels is really just some tuple where all but finitely many of those entries is 0. And so in particular, this will come up in a moment, I can think of evaluating my lambda at some particular prime just by evaluating at the tuple that has 1 in the entry indexed by that prime and 0 everywhere else.
Sorry, I think shouldn't all the finitely many entries should be in the ring of integers, right? Not 0.
Ah, okay, you're right, sorry. Right, and we say, sorry, yeah, so many entries are in, okay. Okay, and we say, we're going to say that it's algebraic. Sorry.
Should be OK star.
So, oh, sorry, OK star. Should be algebraic if evaluation, this is sort of a rough definition. If evaluation at some x looks like locally x to the n for all Archimedean places. Okay, and so for today, what we really want to talk about are algebraic Hecke characters. So I'll add the word algebraic here. Okay.
And you assuming that these types of things are continuous or something like that?
Yes, so this should be continuous.
N is an integer, is that the point?
Yes, n is an integer.
That's why you're not imposing conditions at the non-Archimedean places.
Correct. Okay. And so I want to think about this motivating question in the context of these specific kinds of automorphic representations. And so before I delve a little deeper into the exact question I want to focus on, I feel like I should define a few of the objects that I'm talking about, right? So I'm claiming that I'm going to investigate both the L function attached to some Chow motive and the L function attached to some algebraic Hecke character. So let me start just by saying what these things actually are, so that we can get some feeling for them, right? So for some p, a prime, so now let's switch back to talking about f. Or, sorry, let me keep it at k for the moment, okay? I define the local L factor attached to some choice of lambda, an algebraic Hecke character, to be just, I take 1 minus, now evaluate my lambda at this prime, qp to the minus s, where qp is just the size of this residue field. Okay. And then how do I get, well, so this is the local L factor. And I can similarly get a local L factor attached to a Chow motive so I take my Chow motive, say, over F, right? And now let's consider the system of a tau cohomology given by varying this L, okay? So this gives me a system of Galois representations. And this system will be called a compatible system of Galois representations if there exists some finite set of primes of F outside of which this V sub L is unramified. Okay, and so it's not always clear for any Chow motive that this system will be a compatible system in this sense, but for today, it will happen that we always have this.
You don't ask for some compatibility between the Frobenius stresses?
I don't think so. Okay. And so then if P is not in this S, right, and let's choose an L such that the intersection of L with Z doesn't equal the intersection of P with Z, then I can consider the action of Frobenius at P on this V sub L, okay, at some prime.
So I think maybe part of the definition of compatible should be that this just doesn't depend on L, right?
That what doesn't depend on L?
The action of
The characteristic
the characteristic fundamental Frobenius on that VL.
Okay.
To be defined over some like algebraic closure, like finite extension of Q, then you can talk about independence of L, right?
Sorry, say the beginning of the sentence again.
So firstly, it's like your characteristic polynomial Frobenius a priori is like in QL for each L.
Mm-hmm.
You want it to have a number field such that all the coefficients are in the number field, then you talk about the independence of L.
Okay. Okay. So sorry, you're agreeing with Daniel that.
I agree with Daniel that you need to have the characteristic polynomial Frobenius to be the same, but to be able to justify the word to be the same, like, so you cannot compare a polynomial.
I see. Okay. So let's just say, and the characteristic polynomial is compatible with the action of Frobenius. Is that, you're satisfied with that? Okay. And we won't say what we mean by that. Okay. Okay, so we're going to let Frobenius act on this, which we can do in a compatible way. And now let's look at the characteristic polynomial of this. Okay. Which I'll denote like this. And so then this local L factor of my motive, M, is just defined to be, I take this same QP to the minus 2ns, right? This n and this n are the same. And I multiply that times my characteristic polynomial evaluated at this QP s to the s, okay? So this is, so in a sense, the moral takeaway is that this local L factor is completely determined by just computing the action of Frobenius, and this one is just determined by this lambda, right? Evaluating this lambda at primes. And then what will work about the L functions, we're actually going to talk about the L functions away from this set of bad primes, right? So then we'll take the L function away from this set of bad primes of this lambda, right? This is just going to be the product over all these primes, not in S, this bad set, of these local L factors inverse. And same thing, right, for on this side. So we're claiming that these should be equal, although this is sort of the fundamental question, but we can also take the product over all these primes of these local factors and these inverse, and these are defined, this is defined to be the L function of this motive. Okay. Okay.
And the N is the one defining the type of infinity of the algebraic Hecke character?
This N,
Yeah.
I think this N is just sees the dimension, the like weight of the motive that you're considering.
But it could have different values, or is it fixed?
I think it's fixed. Okay. Okay, and so the idea somehow of the so the idea of the result that I want to present is this. So rather than try to just start with an algebraic Hecke character and produce some motive out of thin air, what if instead we asked, okay, we have this sort of guiding philosophy that I've written over here. What if we started with some modularity result, right? So we started with the information of a motive and an associated algebraic Hecke character, right? And then we try to alter that algebraic Hecke character in some way so that we still have an algebraic Hecke character, right? But we try to do something obvious to that algebraic Hecke character. What can we see happen on the Motivic side, right? And can we do something clever on the Motivic side in order to see that relationship, right? Can we make something explicitly geometric happen on this Motivic side to realize this new algebraic Hecke character? Right, so the idea is, okay, suppose you're handed some modularity result. Okay, this is the data that you start with. And then let's just pick a number. And actually, we want to pick two numbers. Right, but n can really be anything. A is just between n over 2 and n, but symmetrically, we could choose it to be between 0 and n over 2 just as well. Right, so I'm going to fix two numbers. Well, what's the most obvious thing that you can do to alter this algebraic Hecke character? Well, you can take powers of it. You can complex conjugate it, right, and take powers of that. So the idea is just then can you construct a motive, a Chow motive, n, still defined over F, such that now the L function of this new guy is equal to the L function of outside of the same set of bad primes of lambda raised to the a, lambda bar to the n minus a. Okay? So that it's sort of a modularity machine. And that I want this guy to be somehow nicely geometric. Okay. All right, so the theorem, which is joint with me and Jackie Lang, says, okay, we can do this. So we want to start, okay, with a smooth projective variety over some number field F. And now I want the data, the following data. So I want some automorphism of X, maybe possibly after base changing to some bigger field, such that for any element of the Galois group of this F prime over F, I want that there exists some integer such that when I act on this phi by this sigma, it really just raises sigma to some power. Sorry, raises phi to some power. Right, so I'll call this acting by powers. And this might look like a slightly odd definition, but if you think about the example that phi acts on the coordinates of X by multiplication by roots of unity, then this is exactly what happens. Right, when we act by some sigma in the Galois group of this now cyclotomic field, what is that doing? That's just raising each of those roots of unity to some power in a consistent way. Okay. And now I also, right, so I start with my variety and some automorphism, and I also want to start with the data of some motive attached to this variety, right, so in this category, such that, so one, I want this phi, this automorphism of X, to play nicely with this motive, right? So I want phi composed E, the idempotent that cuts out my motive, to just be E composed with phi. 2, I want the eigenvalues of phi on the singular cohomology of my motive to be pairwise distinct. And 3, as I said over there, right, I want to start with some kind of modularity result for this motive, right? So that L, I want to start with the data of some set of primes and some Hecke character such that I have an equality like this, right? And so then the conclusion of the theorem is exactly what I've written over there, right? I can choose any n that I want. I can choose any a less that are between n over 2 and n, right? So really with this choice of a, the only thing I need to rule out is I don't want a to equal exactly n over 2. But otherwise, I can choose any a that I want, and then I can produce for you a motive n realizing exactly this equality, right? And so I should say something maybe about, so actually maybe before I say what n is, let me just do a quick example of a right, you might find all these conditions a little bit annoying, and you might not believe that anything satisfies this set of conditions. So let me just do one example that I claim satisfies all these conditions. Right? Let's consider something like a Fermat hypersurface in projective space. Right? So this is a nice object. Let's call this guy x sub m. Okay. Then what I claim is, okay, so first of all, this x sub m does come equipped with an automorphism phi given just by multiplying any multiplication of any of these coordinates by an mth root of unity is going to give me an automorphism of this thing, right? And moreover, it's a fact that this x to the m, the motive attached to this x to the m, actually decomposes to a bunch of other motives, and each of which will come equipped with an automorphism coming from one of these. Okay, so on each of these I'll have some phi of a. Okay, and then they proved exactly a modularity result for each of these. Okay. And then and one can check that that for any of these, for some of these MA, not all of them, but for many of these M sub A, the eigenvalues of this phi sub A are actually pairwise distinct. So for many A, the eigenvalues of phi sub A are pairwise distinct. This A is somehow a tuple of integers, mod M. And so there's some arithmetic condition on this tuple that will ensure that these eigenvalues are distinct, pairwise distinct. Okay. Exactly, exactly. Okay, so how do I produce this motive? How to construct this guy? It's not so difficult. What we need is a group. We're gonna, as the hypotheses of the theorem imply, we're gonna exploit the action of this phi, right? So we want to use this phi to define a group action, right? So we want to cut this motive n out of x raised to the nth power, right? Because that's so to do that, we're going to define a particular group action on x to the n. So I'm going to define a group G sub n comma a, right, depending on these two choices that I've made, to be, I take phi to the u1 cross phi to the un such that the following condition holds. K, where K is the order of this automorphism, right? So this G is going to live inside of the automorphisms of x to the n base change to f prime. And if you stare at this G for a second, you can convince yourself that this guy is actually just isomorphic to z mod kz to the n minus 1, right? So somehow that each of these has order k, right? So the z mod kz to the n seems normal, but that somehow this condition just cuts you down one copy of z mod kz.
Phi is infinite order. Do you just ask that thing is zero?
I guess you could, yeah. Sorry. I should have said that it was of finite order. Yeah. I mean, this would be an interesting definition. Maybe you could think about this, but I mean to imply that phi is a finite order. Okay, and so then once we have this group, right, we can define the motive of the G invariant motive attached to this x to the n just by the tuple. So this is going to be x to the n. This is all a priori over f prime epsilon, right, where epsilon is going to be, I just sort of average over. This guy should come with this decoration, but I may sort of lose the decoration at some point. This is the graph of this element of G, right? So we're going to we're going to look at all the graphs of these elements of G and then just sum them up and divide by the order of G, right? And so a priori, this guy is only in the Chow motives over f prime, right? But the fact, but this property of this acting by powers means actually, right, that when the Galois group of f prime over f acts on this idempotent, it actually is just permuting these different graphs. Meaning that while the graphs themselves aren't stable under the Galois action, the idempotent overall is, right? So this implies that this epsilon is gal f prime over f stable. So in particular, what that means is that this h of x to the n f prime g, this guy actually lives inside of the Chow motives defined over f. Okay. And so then so the point is that then this n is actually just defined as what I'll write as m to the m to the n G invariant, right? So this is just the pair x to the n epsilon composed with e n times, right? Where e was exactly the idempotent that cut out m, right? And we needed this condition that I've written right here, this number 1 guy, exactly to ensure that this thing really is an idempotent, right? So we need to check that this thing composed with itself is this, right? But that follows because we know that we can commute phi past e, right? So phi can move past e, which will tell us that epsilon can move past e. And then we can just exploit, so we need that this is equal to. Since phi can move past e, we move epsilon past e, use the fact that epsilon and e are both idempotents to begin with, and then reduce to this form. Okay? So that this is the motive we want, and why is this the motive that we want? Right, so what's the key feature of this n, or in why define the group this way, that allows us to make an equality like this? Well, it all boils down, once we've set everything up in this nice motivic framework, it all just boils down to a cohomology computation, right? So you just need to compute the G invariance of the cohomology of m to the n, right? And so the point is that suppose we had a basis for the singular cohomology of m, the guy we start with, given by B1 through BR. Then it will turn out that a basis for the G invariance of m to the n will be given exactly in the form you want for if you hope to achieve an equality like this, right? So that a basis will just look like you take B1, raise it to the a power, then conjugate it and raise it to the n minus a, and do that to every element, BR to the a, BR bar to the n minus a. Okay? And so then, right, why does that essentially prove the result? Well, now that you have these bases, you can use the action of the Galois group and the comparison isomorphisms with a tall cohomology, right, to actually compute Frobenius on the one hand, on the cohomology of m, but also on the cohomology of this n, right? And so on the one hand, so one can compute that this will, so let's compute the characteristic polynomial. If we compute the characteristic we can compute the characteristic polynomial here and write it as some polynomial like that. And then this characterization of the cohomology will tell you that you can compute that actually then the characteristic polynomial of this guy will just look like exactly the same thing, but you do to alpha what you think you should do to alpha. But then we started out with the data that right? We started out knowing that this guy computes L of ms outside of this bad set of primes, and that this guy is equal to L of lambda s, right? So that if you can describe this thing in terms of these alphas, it gives you a way to write this lambda in terms of these alphas, right? And then we come over here and we know exactly what we're supposed to do to these alphas, right? So that then we can, hopefully you can believe me, exactly see this equality show up. Okay, questions up to this point?
Why do you need 2?
So 2 was brushed under this cohomological computation, right? To really see somehow the basis for this guy being in bijection with the basis for this, you want to rely on the fact that these eigenvalues are distinct, and so that they really somehow determine, knowing the eigenvalues determines for you these cohomology classes. Okay, so with the rest of my time, I just want to talk a little bit about how now that one has this nice geometric characterization of this n, one can actually sort of apply this to get some kind of modularity type results for some explicitly geometric examples. So this, one can think of this next part as sort of for people who don't like motives. I'm now going to talk about varieties. Okay, I guess I'll send this guy up and use this board. Okay. So when I talk about these varieties, I'm really somehow talking about, so I'm going to call this modularity, but in quotation marks, for these GNA quotients. And so why do I put modularity in quotes? Well, somehow these are going to be modularity results largely for singular things, right? These quotients will be singular. But still, I think that it gives it's something like a modularity result. Right, so maybe my first example will be, let's let X be some algebraic K3 surface with a non-symplectic automorphism phi, such that if K is the order of phi, so finite order, such that if K is the order of phi, I want the Euler function of K to be equal to the rank of the transcendental part of K. Okay. Then this, what I claim is that this phi satisfies all these conditions where I let now M, my motive, just be the transcendental part of the cohomology of X. And so then Livnet, Schut, and Yui give me a modularity result for this transcendental part of the cohomology. right? And what I claim my theorem implies, right, is that I actually have modularity for t of x to the n g invariance, right, for any, oops, lambda bar to the n minus a, for any choice of n and a that I want.
Capital phi of k, what does that mean?
The Euler phi function. So just the number of integers smaller than it which are co-prime to it. There we go. Okay. Great. So this is pretty much just a direct application of the theorem, right? I'm just using the example of we can take this transcendental lattice of a K3 surface. But it turns out that we can actually do a little bit better in a couple other cases with just some more explicit cohomological calculation. So let's suppose that C is some curve over Q. Phi is some automorphism of C, base change to some cyclotomic field. So this K is, again, the order of phi. Acting by powers on the coordinates of C, right, which we said means that phi satisfies the first hypothesis in that theorem. Now let's let's look at the decomposition of the Jacobian of this curve, right? And suppose that these guys obtain CM, these factors, these isotypic factors in the Jacobian obtain CM by some cyclotomic fields where, moreover, I want to require that these are distinct, these powers be distinct for different I, right? This is just to ensure this second condition over here, okay? Then Shimura and Taniyama have a result on modularity for CM abelian varieties, which gives me this equality of L functions that I want, right? So for any I, I'll have some set of primes, of bad primes, and an algebraic Hecke character, lambda sub I, giving me an equality like this, right? And then our result says that actually so this product equals overall I of these same things that we're used to seeing now, bar n minus a, right? That the Chow motive realizing this thing is actually given by just take c to the n mod g, and then I take the transcendental part of that. Okay. So that this is maybe a sort of more compelling geometric example, right? That somehow this feels very explicitly geometric. C to the n mod g, just taking the transcendental part. The cohomology.
Are you mean like in the middle cohomology?
So in fact, the way we've set this up, this c to the n mod g will have a Hodge diamond that looks just like this. So there will be if this is the genus of the curve, a g in this a and minus a position, and then the mirror one over here, and everything else will be 0. Right? So when I say the transcendental part, I don't even need to specify what degree I care about. I can just sort of, and in fact, everything here will be algebraic. So I can just kill the middle. Yeah. Okay. And so And so as two sort of further curve examples of this example, if we look at, say, elliptic curves with Cm by Q adjoin zeta 3 or Q adjoin I, one can check that they satisfy all these hypotheses. And in fact, a result of says that there exists a smooth model Y of this quotient that we consider. So when n equals A. Of this quotient we consider such that this Y is a Calabi-Yau n-fold. And then they actually prove this modularity result that we prove. So our result recovers their thing. And I mean, I should say that this result is really sort of independent interest for people who care about modularity of Calabi-Yau varieties, right? That people are very interested in being able to compute things like the periods of Calabi-Yau varieties for sort of physics interests, and those can be recovered by knowing the L function attached to it. And then 2b is actually that any curve that looks like this, gamma x, so any planar curve of this form where these exponents are bigger than 2 and are coprime, and I said this thing should be defined over Q. Any curve of this form also satisfies this set of hypotheses. Okay, so it's really not so obscure, a list of conditions. And then lastly, I guess, if you want one more example that looks sort of explicitly modular. Let's say we have some simple abelian variety over Q with an automorphism of order K, such that phi of K is twice the dimension of A, right? So A has Cm by this phi, induced by this phi. And moreover, I want this phi to acts by primitive roots of unity on the coordinates of A. By which I mean think of A as a complex torus, right? So think of it as a quotient of C to the whatever mod some lattice, and now think of phi acting on those coordinates in this complex, in these complex coordinates. Right, then in fact, so again, we have this modularity result just from this result of Taniyama and Shimura for Cm abelian varieties. And then again, after a little bit of computation with cohomology, one can actually check that, outside of some bad prime, that the motive we get is just H1 of A to the n mod G. So for example, what's an abelian variety that satisfies these conditions? Well, let's look at the Fermat curve of degree m in P2. Right, and let A be any simple factor of the Jacobian of this curve. Okay, and then we'll get a result like this. So these examples were all just somehow to see that really you can realize these sorts of results in some explicit geometric way. You won't a priori get an actual variety, but you'll get something that feels a little more intuitive than some abstract Chow motive. So yeah, I think I will end there.